In the previous video, we invented the complex numbers. Our goal was to solve more equations, and we just invented the solutions to those equations. We started doing calculations with our new numbers, and we quickly concluded that they are essentially two-dimensional. But this feels like a cheap trick. Instead of just inventing numbers with exactly the properties we need, we would like to follow a more rigorous approach. So here's what we will do in this video. We will turn things around. The goal that we start from will be to find a 2D number system that extends the 1D real numbers in the best possible way. Framing the question like this, we can discover all the different possible 2D number systems and compare them to the one we invented earlier. How many 2D number systems are there? Are they similar to the complex numbers or totally different? Which one of these new number systems is the best one? There are two ways to approach this. One way is to use the algebra of the real numbers to guide our search. We will do that in the final chapter of this video. The other way is to use geometry instead of algebra. We will study the geometry of the real numbers and then figure out how to extend it to more dimensions. Let's follow this geometric approach first. The real numbers are often visualized as points on a line. The number 0 is at the origin. What you don't often see is a visual explanation of the operations like addition and multiplication. What is their geometric effect? Addition is easy. Just picture each number as an arrow that points from 0 to the numbers point on the line. Positive numbers point to the right, negative ones to the left. To add two numbers together, you just put one of the arrows behind the other, and then you follow both, starting at the origin. This is probably the easiest way to understand how addition of a positive and a negative number works. 3 plus minus 5 is minus 2. Now watch what happens when we apply an addition to all numbers on the line at once. I'm giving the point at 0 a bright yellow color so that you can follow where it goes. It's the neutral element for addition, so when you add it to any x, you just get x itself. For example, adding 3 to all real numbers shifts the points to the right by 3 units. The yellow dot lands on the number 3 itself because 0 plus 3 is obviously 3. Similarly, adding minus 5 to all the points shifts them 5 units to the left, and the yellow dot lands at minus 5. So addition can be visualized as translation or shifting. All the points on the line stay a fixed distance away from each other. They all shift to the left or the right together. Each number is an arrow that pushes everything along its direction over the length of its arrow. If arrows remind you of vectors, that's no coincidence. The addition of real numbers is the addition of vectors. The vectors just happen to live on a very boring one-dimensional number line. When we extend our number system to 2 dimensions, it's very natural to keep using vector addition. After all, the sum of two vectors in 2D is calculated exactly as we just did for the one-dimensional real numbers. You place one vector after the other, and then you start at the origin and follow the arrows to reach the resulting sum. If you follow the vectors in the alternate order, you get the same result. That's because vector addition is commutative, which means that a plus b always equals b plus a. This is where that famous parallelogram rule comes from. Just like we did before, we can now apply a specific addition to all points on the plane. For example, adding the real number 3 to all other points shifts the entire plane to the right by 3 units, just like it did on the real number line. But this time, we have an extra vertical dimension to play with. Adding the vertical number 3 to all points shifts the plane up by 3 units. And adding the number with coordinates 3, 2 shifts everything to the right by 3 and up by 2. Note that the neutral element 0 ends up at 3,2. So even if I showed you only the end result of the shifting process, you could still figure out what happened along the way. Good. So it seems to make a lot of sense to use two-dimensional vector addition for our new number system. And guess what? That's exactly what we already discovered in the previous video, where we figured out that each complex number can be written in the form a plus bi. Watch as I introduce a dummy 1 in the formula here. This makes it clear that our number is actually a linear combination of two basis vectors, the real unit 1 and the imaginary unit I. So each complex number really is a kind of two-dimensional vector. The real and imaginary parts of the number are the horizontal and vertical components of the vector. And when you algebraically add two complex numbers together and then regroup the terms, you end up adding the real parts separately and the imaginary parts separately. That's exactly what vector addition also does. It adds the x components separately and the y components separately. So the complex addition formula matches precisely with vector addition. Conclusion so far: two-dimensional addition is easy. We can just use vector addition. This extends the addition of the real numbers perfectly because both are essentially the same thing. They both translate or shift. They both involve placing one arrow after another and following them. This corresponds exactly to the addition of complex numbers we discovered earlier. And the identity element is still 0 in both cases. Great! Addition is now out of the way. Next, we turn to multiplication. On the real number line, multiplication can do a few different things. First of all, it can stretch numbers away from 0. If you double the number 3, it moves twice as far from the origin. If you double the number -2, it also moves twice as far from the origin. So the geometric interpretation of multiplication by 2 is that it stretches the number line out, leaving each number at twice its original distance from 0. This time I painted the number 1 bright yellow, because it is the neutral element for multiplication. So when doubling all the numbers, the yellow dot lands on the number 2. Note that 0 itself does not move, no matter what you multiply it with. That's simply because 0 times anything is 0. Similarly, multiplication by 3 stretches everything 3 times farther from the origin, and so on. We can also multiply by 1/2, which is the same as dividing by 2. This time the real number line shrinks, because every point moves closer to the origin. 0 itself stays in place, just like before. So, multiplication can stretch and shrink all the real numbers, but there is one more possibility, and this turns out to be a very important one. Let's see what happens when we multiply by -1. Because the sign of every number flips around, the numbers rotate 180 degrees around the origin. So, besides stretching and shrinking, multiplication can apparently also rotate. It always rotates by 180 degrees, so that the number line stays horizontal. And just like before, the origin stays in its place. After all, 0 times -1 is still 0. By the way, if I multiply by -1 and then by -1 a second time, everything goes back to its original position. The net result is as if I had not done anything at all, which is basically a multiplication by 1. This is the geometric reason why -1 times -1 is +1. Two rotations of 180 degrees cancel each other out and leave everything in its original position. We can use our geometric interpretation to verify many of the well-known properties of the operations. For example, say I multiply by -2. I can do this in two ways. first stretch by 2 and then rotate 180 degrees. Or I can rotate first and then stretch by a factor of 2. The result is exactly the same. Why? Because multiplication is commutative. The order of multiplication does not matter. Okay, now it's time to introduce the vertical axis. Remember, we want to extend multiplication from the real number line to the entire plane in a consistent way. So we have to make sure that we can keep stretching, shrinking, and rotating in 2 dimensions. We can start from our 2D vector space again. Apart from addition, vectors also support scalar multiplication, which is basically multiplication with a real number. The effect of scalar multiplication is that it stretches and shrinks vectors, and that's exactly what we want. For example, if we multiply all vectors by the real number 2, we essentially double their length, stretching them all away from the origin. Focus your attention on the real number line, and you'll see that the dots only move horizontally. So multiplication has exactly the same geometric effect on the reals as before. The reals are nicely embedded inside the 2D plane. That's nice. And again, we can verify some properties. For example, when we multiply by 2 and then by 1/2, the net result is that we did absolutely nothing, which is a multiplication by 1. So the numbers 2 and 1/2 are still each other's inverses. Great. What happens when we multiply by -1? Well, when you multiply a vector by -1, it flips around the origin, turning into its own opposite. This happens to all vectors at once, so this time the entire plane rotates 180 degrees around the origin. Nothing special. But we also want to be able to multiply with numbers that are not on the real number line. What would multiplication with a number like I look like? This is where the yellow dot becomes important again. Remember 2 things. 1 times I is just I itself. And 0 remains in place, no matter what you multiply it with. So in order to multiply everything in the plane with I, we have to fix the origin in place, and then we have to move the number 1 to the number I. 3 Blue on Brown has a great video where he shows more examples. His trick for visualizing complex multiplication is that you pin down the origin so that it can't move, and then you move the neutral element, the number 1, to the target point. The rest of the plane moves along, stretching or shrinking or rotating as needed. There's a link to his video in the description. When we apply this cool visualization trick, we see that the multiplication with I boils down to a rotation of 90 degrees, counterclockwise. You rotate the number 1 to the number I, and the rest of the plane rotates along. Let's try a few more examples. Multiplication by this number here causes a 45-degree rotation. And multiplication by -1 causes a 180-degree rotation, just as expected. As a final example, multiplication with 2i will rotate the plane 90 degrees and scale everything by a factor of 2. Again, the fact that multiplication is commutative allows you to do this in 2 steps. Either rotate first and then stretch, or stretch first and then rotate. The result is the same. So the geometry of multiplication still consists of stretching, shrinking, and rotating, just like it did for the reals. But we now get rotation over any angle, not just 180 degrees. This turns out to be the most natural extension of one-dimensional real multiplication to two-dimensional multiplication. Now that we've discovered that complex numbers love to rotate, this might remind you of polar coordinates. Every complex number can be written in polar coordinates with its length and the angle it makes with the horizontal axis. The length of a vector is called its norm, but for a complex number people usually prefer to call it the modulus. It's always a positive real number, or 0 for the number 0 itself. You write it with vertical bars around the complex number. It's also often written with the letter r. The angle of a complex number is often written with a Greek theta. It isn't too difficult to go back and forth between polar coordinates and rectangular coordinates. Just use Pythagoras and the definitions of sine and cosine. This allows us to write a complex number as r times the cosine of theta plus I times the sine of theta. The cosine takes care of the horizontal real part. The sine gives us the vertical imaginary part. The reason we switch to polar coordinates is because they make rotations much easier to express. Complex numbers are all about rotations in the plane, so we want to use the coordinate system that makes this as trivial as possible. For example, you can easily do a rotation by 90 degrees by just increasing the angle of your complex number by 90 degrees, or pi over 2. Its length stays the same. This makes things a lot easier. Polar coordinates also allow us to link the geometric and algebraic perspectives. I mentioned that it's easy to convert between polar and rectangular coordinates. Let's do that conversion for the product of two complex numbers. I use complex numbers with a modulus of 1 to make things easier. Because multiplication is rotation, the resulting product is a number that has the sum of the angles, theta 1 plus theta 2. You can then apply the rules for the cosine and sine of a sum, which you may remember from trigonometry. You end up with exactly the formula for the complex product that we found in the previous video. Everything works out exactly as planned. That's good news. It means that our new geometric interpretation corresponds with the algebra we already established earlier. Pause the video if you want to check the details. And now for the big payoff. Look at what happens when we multiply by I, and then multiply by I again. This gives us a rotation of 90 degrees, followed by another rotation of 90 degrees. The net result is a rotation by 180 degrees, which lands at the number -1. That is the geometric reason why the number I squares to -1. We have finally figured out what I is, geometrically speaking. The number I is a rotation by 90 degrees. Or more precisely, the number I, when multiplied with any other number, rotates that number over 90 degrees. We can now draw some conclusions about the geometry of the complex numbers. Addition is just vector addition, causing a 2D shift of the plane. Rectangular vector coordinates are perfect for this purpose because you can just add the real and imaginary parts separately. The identity element for addition is still the real number 0. For multiplication, it is better to use polar coordinates. That's because multiplication rotates the plane, as well as stretching and shrinking it. This is a natural extension of what the real numbers already did, only this time we can rotate over any angle we want, not just angles of 180 degrees. The identity element for multiplication is still the real number 1. Perfect. And we did not have to invent this number system at all. It's a natural two-dimensional extension of the one-dimensional real numbers. Okay, now that we have a solid geometric understanding of the complex numbers, let's return to their algebra. Addition is easy, so I want to focus on multiplication here. I would like you to come away from this chapter with a feeling that you could have discovered the multiplication of the complex numbers from scratch, with a bit of patience. Your mission is to find the best possible multiplication for a 2D number system. In particular, we want all of the well-known algebraic properties of multiplication to remain valid in 2 dimensions. We should find a multiplication that is associative, has the real number 1 as its identity element, has inverses so that we can also do division, distributes over addition, and so on. This is a tall order, and it won't be easy to meet all of these requirements. But let's agree that the more of these properties we can satisfy, the better our number system is. So let's get creative and try a few different options. I give you 2 two-dimensional numbers with their rectangular coordinates AB and CD. The goal is to come up with a brand new formula for their product. Here are a few possible examples. You can get as crazy as you want. There are many more possibilities. We won't have time to explore all of them, but here are a few of the more interesting ones. Our first attempt keeps the x and y coordinates strictly separated. This is very similar to how addition works. Just create a new 2D point with the combination of the x coordinates as its x coordinate and the combination of the y coordinates as its y coordinate. At this point, the properties of real multiplication simply transfer to this new 2-dimensional multiplication. For example, each coordinate is a commutative product, so their 2D combination is also commutative. You also get division for free and an identity element. But here we hit a snag. The identity element for this new multiplication is the number 1, 1. That's cute, but it isn't what we want. We want to extend the real numbers, where the identity element is the number 1 here, not this other number here. So we need a product for which 1, 0 is the identity element. Honestly, even without that particular snag, this number system is also kind of boring. It's basically just 2 separate copies of the real numbers that you stick together. There are no interesting interactions between the x and y axis. We don't discover anything new. Let's try something else. Here's a product that mixes the x and y coordinates together. But if you fill in 1, 0, you'll see that it still doesn't work as an identity element. Okay, we try again with a different example. Fill in 1, 0 and aha! This time, our preferred identity element does its job. Good, now we're getting somewhere. Let's check another important property. We want to be able to divide our new numbers, not just multiply them. So, we need each number a, b to have an inverse, 1 over a, b. I won't go into the details here. Pause the video if you want to check the calculations yourself. It turns out that division fails. The reason is that this expression in the denominator can be 0 for many non-zero numbers, so we will never be able to divide by those numbers. Well, I hope you're beginning to realize just how difficult it is to construct a well-behaved multiplication. But let's not give up just yet, we're actually really close now. If we could only change this minus sign into a plus sign, the denominator would always be positive. Well, except for division by 0, of course, but that's an acceptable exception. Tracing back to where this minus sign comes from, we find that we should change this plus sign into a minus sign. Et voilà! A new and improved multiplication formula. You can check that division works just fine this time. That's because we have a plus sign in the denominator here, so we will never divide by 0, except when dividing by the complex number 0 itself. You can also check that 1, 0 still works as the identity element. Wow, have we finally done it? Have we found a 2D number system that extends the reals and satisfies all the necessary algebraic properties for a product? Yes, we have. Congratulations. Party time. Now do yourself a favor and calculate the product of the number 0, 1 with itself. Just set a and c both to 0 and b and d both to 1 and calculate the resulting coordinates. Really, try it now. I promise that it's worth it. I'll wait. Okay, did you do the calculation? Were you shocked that the number 0,1 squares to -1,0, which is basically the real number -1? So we have a number that squares to -1. That's exactly the definition of I. It even has a horizontal or real part of 0 and a vertical or imaginary part of 1. Would you believe that after all this effort, we've just rediscovered the complex numbers? Actually, you probably already recognized this formula from an earlier video. It's exactly the formula for the complex product, written with coordinates instead of as a linear combination with I. But it's essentially the same formula. Addition and multiplication have to satisfy a whole host of properties. You have now experienced firsthand that finding a formula that satisfies all these properties is not easy. It turns out to be so difficult that only one formula does the trick. Mathematicians have been able to prove that no other formula exists that has all of the nice properties we want. Even in other dimensions higher than 2, no perfect multiplications can be defined. We will get back to that later when we look at other higher dimensional number systems. By now, I hope that you realize that the complex numbers are the ultimate, inevitable, unique, and most natural 2D number system out there. We didn't need to invent them. We could have discovered them from scratch because they are the only game in town. The properties of geometry and algebra both guide us directly to the complex number system. Each perspective offers new insights. Each also has its pros and cons. Choose wisely and you can learn to wield these perspectives as powerful tools. Our journey so far has given us 2 different perspectives on the complex numbers. The algebraic perspective shows us how important the rules of algebra are. Those rules help us when looking for well-behaved mathematical objects and systems. They help us find the best formulas for addition and multiplication. The complex numbers allow us to solve all algebraic equations. This finally puts an end to the story of nested number systems. This is why C is called algebraically closed. And then there is the geometric perspective. The real and imaginary part act as coordinates of a 2D point or vector. These rectangular coordinates are good for understanding the addition of complex numbers. Polar coordinates are better for multiplication. In polar coordinates, you clearly see that complex multiplication is all about rotation. And this is where complex numbers really shine. Everything that rotates in physics and engineering can be studied with complex multiplication. In the next video, we dive much deeper into the geometry of rotations. In the meantime, I've left a few links in the description so you can continue your research. Remember that my videos only give you a high-level overview. I always try to point you to the best learning materials so that you can study the complex numbers in more detail. If you don't want to wait for my next video to be released, the entire series on complex numbers is already available right now over on Patreon. The easiest way to support the channel is to subscribe, like this video, and share it with other nerds who also love mathematics. Thank you, I really appreciate your support.